as a means of review, let's go ahead and look at On Your Own 8.4 again. I think we finished the class with this the last time. We're looking at calcium carbonate, which the problem says is a substance used to melt. Actually, it's the calcium chloride 6 hydrate that is used to melt snow. You guys wouldn't know a lot about that, but where I come from, we got this stuff all over the place, okay? Is used to melt snow on streets and sidewalks. It's made from calcium carbonate using this reaction that's listed on the board. If 7.2 moles of hydrochloric acid are added to excess calcium carbonate, the phrase excess calcium carbonate, how much do you have if you have excess? Got plenty. Don't worry about it. Don't worry about how much you have because you've been told you've got plenty. What they're doing when they say this is that they're letting you know what your limiting reactant is going to be, okay? It's mixed with excess, let's see. If 7.2 moles of hydrochloric acid are added to excess calcium carbonate and excess water, so your whole reaction, your whole mole ratios are going to be based on the balanced equation, but the amount you actually need is going to be limited by the amount of calcium carbonate. They've made that the limiting reactant by saying you've got plenty of this and plenty of this. So we're only looking at the amount of this. If 7.2 moles of hydrochloric acid are added to excess calcium carbonate, excuse me, I got it backwards. This is the limiting reactant. How many moles of calcium chloride 6 hydrate will be made? Now, big terms, big names, big symbols, process-wise and concept-wise, it's the same thing we've been doing for the last module and a half, okay? As you look at the balanced equation, we have a name for the coefficients. We used to just call them the coefficients. And here the coefficient was an implied 1, a 2, a 5, an implied 1, and an implied 1. This chapter, we added something to that. It's not just simply a coefficient. It's the stoichiometric coefficient, right? The stoichiometric coefficients are the ways for us to understand the relationship in terms of the ratios of each of these molecules in terms of reactants or product. Remembering that we can figure out any one of these, like if we have the balanced reaction equation with the appropriate stoichiometric coefficients, if we know one amount, we know the amount required for the perfect recipe, the perfect reaction, for every amount. We could compute, given a certain amount of hydrochloric acid, how much we would need of calcium carbonate and how much we would need of water based upon the stoichiometric coefficients. But this problem is telling us we've got plenty, so we don't have to compute them, right? If they told us we had a certain amount of hydrochloric acid and a certain amount of water, we would have to maybe figure out which of those was the limiting reactant and then base our reaction on that one. Now, a phrase that is in the book, and you may hear, I haven't used it a lot, is this idea of mole ratios. I have been telling you that the stoichiometric coefficients represent the relationship between the number of moles of everything. That's sometimes referred to as the mole ratio, okay? Whenever we write our problems and we solve it and we have the 2 to 3 or the 1 to 4 or whatever the relationship is, that is the mole ratio. So don't let that term stumble you. If you see that term again, what is the mole ratio? What I'm talking about is 2 to 3, 1 to 4, 7 to 9, whatever the relationship is based upon the stoichiometric coefficients. So if we were told in this case that we have 7.2 moles of hydrochloric acid and we're trying to figure out how many moles of calcium chloride 6 hydrate would be made, we're intentionally leaving a gap here because we're going to fill this in with a piece of information, actually time permitting, either today or tomorrow. We're going to start working not from moles, but from grams, and moving from grams to moles to moles, and then back up from moles to grams. In this case, 7.2 moles of hydrochloric acid, and we're computing how many moles of calcium chloride 6 hydrate. Now, the relationship between these things as we're moving from 7.2 moles to however many moles we're trying to compute, from our known to our unknown, they're going to relate to one another in this mole ratio, this relationship of 2 to 1. Now, where does that relationship 2 to 1 come from? The stoichiometric coefficients that we find in the balanced reaction equation in front of the molecules that we are given in terms of our known and our unknown that we're solving for. So this 2 to 1 comes from hydrochloric acid, the 2 in hydrochloric acid here, and we're trying to solve for moles of calcium chloride 6 hydrate. The implied 1 in front of that molecule is where this 1 comes from. And so as we move from our known to our unknown, we know that the mole ratio is 2 to 1 in terms of hydrochloric acid to calcium chloride 6 hydrate. But our multiple in this case, since we're moving from this to this, our technique, we come across, hit the first number, it gets driven to the bottom, so our multiple is 1/2. What this is telling us is whatever number of moles of hydrochloric acid we have, we're going to produce half that much, or we've got the potential to produce half that much of calcium chloride 6 hydrate. So 7.2 times 1/2 gives us 3.6 moles. All right? Now, in this equation, as we look at the stoichiometric coefficients up to this point, what have we said we can relate based upon the stoichiometric coefficients? What am I actually relating? You said moles, right? What does a mole represent again? A counting unit. So it's how many of each thing, how many pieces, right? How many, in this case, molecules? How many molecules of hydrochloric acid relate to how many molecules of calcium chloride 6 hydrate? We could do it at the 1 level. We could also do it at the dozen level. We could do it at the 100 level. We could do it at but ultimately we do it at the molar level, a mole, using Avogadro's number of 6.02 times 10 to the 23rd of them. It's a huge number because it's in the range that we can actually measure out and see and do something with. And I've said repeatedly that what we cannot do is what? These relationships do not relate, correct, they do not relate grams to grams. Now we're going to do that. We're going to start working from grams to grams and using moles as our translation process in the middle. Before we do that, the next section in the book is talking about volume relationships for gases in chemical equations. And this is one of those exceptions. We've been talking so much about the stoichiometric coefficients in our balanced reaction equation representing pieces or counts, making sure that you don't get it confused and inadvertently use grams. If I gave you how many grams of hydrochloric acid, you would not simply multiply by 1/2 to get the grams of calcium chloride 6 hydrate. That would not be true. But there's an interesting rule or interesting law we have, and whether you pronounce it Gay-Lussac's rule or Guy-Lussac's rule, we all know, because we watch plenty of hockey, that Guy is actually G-U-Y. We say Guy, but it's pronounced Guy in a good French Canadian kind of way of saying it, right? But Gay-Lussac, and that's our new module here, is about these volume relationships for gases in chemical equations. And we have this law, Gay-Lussac's law. It says the stoichiometric coefficients in a chemical equation relate the volumes of gases in the equation as well as the mole ratios of all the substances in the equation. We're kind of adding one little wrinkle to what we've already learned. We know that the stoichiometric coefficients represent the number of moles of every single molecule in the balanced equation. We can now add to that a little piece of knowledge that says not only do the stoichiometric coefficients relate to the volume, the count, usually in moles, but it also relates to the volumes of the gases, but only the gases. If we look at this reaction equation up here, we've got hydrogen and nitrogen reacting together to produce ammonia. Okay? All three of those molecules on the board are gases, and this is where the phase symbols become vitally important. Because Gay-Lussac's law can only be applied to gases. This little wrinkle, caveat, corollary, however you want to think of it. This little difference only works for the gases. In this case, all three of them are gases. And so if we weren't talking about Gay-Lussac right now, I look up here and say, okay, 3 hydrogen molecules react with one nitrogen molecule, to produce 2 ammonia molecules. Or 3 dozen hydrogens react with 1 dozen nitrogens to produce 2 dozen ammonias. Or 3 moles of hydrogen and 1 mole of nitrogen react to produce 2 moles of ammonia. We'd be hopefully very comfortable with those kind of statements coming from me right now. Okay? Moles to moles to moles, the mole ratios. With Gay-Lussac's law, we can also say 3 liters of hydrogen reacts with 1 liter of nitrogen to produce gas. What does it produce? 3 liters and 1 liter react to produce 2 liters of ammonia. Okay? So Gay-Lussac is only looking at the gases in the reaction, and it relates the volumes. And it can be any volume unit. So it's a 3-dimensional unit. It's liters, it's cubic centimeters, it's gallons. Whatever your unit is, it's a volume unit. It relates the volume of one gas to the volume of every other gas. Just as we used moles before, we can do the same thing with Gay-Lussac, looking at volumes. Use an example here. In this case, we've got acetylene gas reacts with hydrogen gas to produce ethane gas. I could say that 1 mole of acetylene reacts with 2 moles of hydrogen to produce 1 mole of ethane. And with Gay-Lussac, because they're all 3 gases, I can also say that 1 liter of acetylene reacts with 2 liters of hydrogen to produce 1 liter of ethane. See, there is no such thing as conservation of volume. I have 1 liter and 2 liters, that makes 3 liters of gas. When I combine those 3 liters of gas, it makes 1 liter of ethane. There's no such thing as conservation of volume. We do have a conservation of mass, but the relationships here are molar, and in this case, because they're all gases, it's also volumetric. 1 liter and 2 liters react to produce 1 liter. Now, granted, this would be a much denser, right? Because there's more mass in a much smaller volume than the 3 liters here altogether. But still, in terms of if you captured it, how much would you get? You take 1 liter and 2 liters to produce 1 liter. However, if we look at this equation here, calcium oxide and hydrochloric acid react to produce calcium chloride and water. In this reaction here, I could go through and say 1 mole of calcium oxide plus 2 moles of hydrochloric acid, they react together to produce 1 mole of calcium chloride here and 1 mole of water. If I were to try to apply Gay-Lussac's law to this equation, what are the only things that I can relate? When we talk about moles, we can relate everything to anything else. When we talk about Gay-Lussac, we can only relate gases to gases. In other words, here I could say, in this reaction equation, if I assume that I have 2 liters of hydrochloric acid gas, in terms of 2 liters, I can't say anything about my calcium oxide or my calcium chloride. And why not? Why can't I tell you about the volume of calcium oxide or the volume of calcium chloride in the reaction? They're not gases. Gay-Lussac does not help me in this case with my calcium oxide, and it doesn't help me with my calcium chloride. It does help me, however, with my hydrochloric acid, this gaseous hydrochloric acid, and my water vapor, my gaseous H2O. I can say that 2 liters of hydrochloric acid will react with calcium oxide, if it has sufficient calcium oxide, to produce 1 liter of water vapor, of gaseous H2O. So when we're using Gay-Lussac, the only things we can relate are the gases, and the only time we use it is when we're trying to relate volumes. We will be able to go and say, for example, I've got a volume of this gas, how many moles does that represent? We'll convert that later on. We'll convert liters to moles, and then once we have it in moles, we can relate moles to moles. Because, again, when we're relating moles, we can relate all the coefficients, which represent all of the molecules. When we're using Gay-Lussac, we can only relate the volumes of gases to one another. Okay? Any questions on that? Yes, sir?
So we'll still be able to say we have 2 moles of HCl?
Yes. Yeah, in terms of moles, it still works. It works for everything. The balanced reaction equation works for every molecule in the equation in terms of moles. It simultaneously works, because of Gay-Lussac, it simultaneously at the same time works for the volumes, but only for the gases. You can't look at the solids, the liquids, the aqueous, just the gases. So if I ask you a question and I have something in there that is a gas, up to this point, really, you haven't really cared about it, right? Because we've only been talking about moles. And up until this point, I often will write an equation on the board and just drop the phase symbols, because to this point, it hasn't really mattered. Going forward, however, it will matter. Going forward, I may ask a question relating the volume of one thing to the volume of another, and you can only do it if it's a gas, which means it has the G phase symbol. If I give you the volume of hydrochloric in this reaction, and I ask you to give me the volume of calcium chloride, the response is, Gay-Lussac doesn't allow me to do that. I can't do that. I can only relate the volumes of gases in the equation. But at the same time, it's still true that the coefficients always represent the moles of every molecule in the reaction. Example 8.5 is on page 288 in the third edition. It says, an automobile engine burns gaseous octane. If an automobile completely combusts 12 liters of gaseous octane in excess oxygen, how many liters of carbon dioxide will be produced? So the problem asked us to completely combust octane. You should remember from the previous module that to completely combust means that I'm going to react it with oxygen. So I've got my octane and oxygen, and complete combustion is going to be a carbon, hydrogen, oxygen chain, reacts with oxygen to produce carbon dioxide and water. Okay, so this is where previous learning from the other module, completely combust octane, boom. And this is the basic equation. What do I have to do now? Balance it, right? When you go through the balancing process, this is what you come up with, that there are going to be 2 octane reacting with 25 oxygen to produce 16 carbon dioxide and 18 water. Also notice that every single molecule in here is in the gas phase. So we can not only apply 2 moles reacts with 25 moles to produce 16 moles and 18 moles, but because they're all gases, we could also say that we could react 2 liters and 25 liters to produce 16 liters and 18 liters. Since they're all gases, it applies to every one of them. If there were some solids, some liquids, some gases, we could only relate the gases in terms of volume. But we can always relate the molecules in terms of the mole, the stoichiometric coefficients. So we're told that we have 12 liters of gaseous octane, and we're going to react it. How many liters of carbon dioxide will be produced? We were told we have excess oxygen, so we're not concerned about oxygen potentially being our limiting reactant. We know that the octane is going to be our limiting reactant because we have plenty of oxygen. Our setup is going to look exactly like as if we're working with moles. We have 12 liters of octane, and the question is, how many liters of CO2 are produced? Working across from left to right, our mole ratios, or in this case, our volume ratio. Okay, the ratio of the volumes is going to be the same as the ratio of the moles. And as we look at our balanced reaction equation, not our initial, look at our balanced reaction equation, the stoichiometric coefficient for the octane is a 2, and the stoichiometric coefficient for the carbon dioxide is a 16. So they relate 2 to 16 for their mole ratio. And as we're moving from left to right, we can see that the 2 gets bumped below the 16, so we have a multiple of 8. Let's look up here. Does that make sense? 2 to 16. If I multiply 2 by 8, what do I get? 16. Okay, that makes sense. I'm multiplying by 2. Because they're both gases, we can use Gay-Lussac and say, okay, rather than moles, I'm going to use liters. 12 liters produces how many liters of carbon dioxide? That's 96. 96 liters of carbon dioxide are produced in this reaction equation when we use 12 liters of octane. 12 liters of octane have plenty of oxygen. There's excess oxygen. It will produce the full reaction equation in those ratios. 2 to 25 produces 16 to 18. 16 and 18. So 12 liters produces 96 liters of CO2. Okay? So if you understood the process for moles, this is just one little wrinkle, one little caveat, that rather than moles, you can use liters, but make sure that what you're relating here to here, they're both gases. I failed to put gases over there on 96 liters of CO2, but it should be 96 liters of CO2 gas. On your own 8.5. Start working it at your seats. A chemist decides to produce carbon dioxide gas using the following reaction equation. Na2CO3, HCl produces 2 Na sodium chloride, carbon dioxide, and water. Okay? If the chemist wants to make 8.2 liters of CO2 gas, how many liters of hydrochloric gas must be used? We'll walk through it as soon as he gets back. Does everybody have an answer? An answer? Okay. Almost there? Good. Is it? Yes, it is. Yeah, normally when they give you an equation with some stoichiometric coefficients in it, it's going to be balanced, but I checked it as well. It is balanced. So. I'm just going to go ahead and erase what I've written on the board because it'll conflict with the PowerPoint slide when I start revealing it. So, trying to produce 8.2 liters of carbon dioxide. How many liters of gaseous hydrochloric acid would we need? Is everybody feeling comfortable with this process? I mean, we've seen it enough times, okay? First step, if we don't have the balanced equation, if we are given, like in the case of octane, combust octane in excess oxygen to produce carbon dioxide and water vapor, we write down the basic equation, then we balance the equation. We should do that all the time because our relationships are based upon the balanced reaction equation. That's where we get our true stoichiometric coefficients. Then, if we're working with grams, which we will be in a moment, we would write them right below. But in this case, since we're working with either liters or moles, we're going to bring it down a little bit, leave ourselves some room. Since we don't need to do those steps in this problem, it's a much simpler problem. So we've been asked how many liters of hydrochloric gas would be required in this reaction to produce 8.2 liters of CO2. In this case, we're working from right to left, and below that we need to know what are the mole ratios. What's the relationship? The liters of hydrochloric acid and liters of carbon dioxide. We go back to the balanced reaction equation, and we know that in this equation, the stoichiometric coefficients apply for every molecule when we're talking about the number of moles, but they also apply for every gas when we relate them to another gas. In this case, we're relating liters of hydrochloric acid gas and liters of carbon dioxide gas. So yes, we can use the same mole ratio, the same relationship as we would have if we were talking about moles. What is that relationship? Well, it's 2 to 1. The relationship is 2 to 1. And since we're working from right to left in this case, our multiple is 2. It takes twice as much hydrochloric acid to produce an amount of carbon dioxide. Does that make sense from the balanced reaction equation? Twice as much hydrochloric acid as carbon dioxide. Yes, that makes sense. In this particular case, we've been asked to produce 8.2 liters, and so we require 16.4 liters, twice as much. So this gives us our statement of reality. This tells us, okay, these are the way they relate to one another all the time in proportion. Given this specific amount, how much specific amount do you need? And they follow in the same proportion. Okay? Everybody comfortable with that? Okay, remember, it's only gases. Gases are the only thing you can relate using Gay-Lussac. And you can simultaneously, back to your question, you can simultaneously use it for moles for every molecule in the reaction. Okay. Actually don't have a lot of pre-made slides on these other than the reactions, because we're going to get in, it takes a long time to create these slides because there's more steps, and they're vertical steps in PowerPoint. I didn't take the time to do that for the slides. So we're going to actually work through these equations, and I'll put them on the board, but we're going to use more marker than we have the last couple times. We're going to take our balanced reaction equations, which we've been using now to relate moles to moles, and we're going to change it because we're going to add the, yes sir, you may. We're going to change it now to, we're going to relate grams to grams. And as I said before, we've already discussed the fact that we use the relationships here, the molar relationships. They relate moles to moles, count to count, number to number. They do not relate grams to grams. They do relate, we just learned now, they do relate liters to liters for gases. Okay? So they do relate moles to moles for everything. They do relate liters to liters for gases, and gases only. But again, we don't typically go over and measure out, we don't have a device that goes and measures a mole. We have devices that go and measure out grams, masses. And so we need to translate from mass to moles so that we can use the balanced reaction equations to translate from one amount of moles of one molecule to the number of moles of another molecule, and then oftentimes translate that number of moles back into a unit we actually measure in terms of mass or grams. And so that's what we're going to do now. We're going to add that step, that intermediate step. To give this equation over on, this is example 8.6. A chemist needs to produce 100 grams of gallium trichloride. Here's the gallium trichloride. Now, if I told you the chemist wants to produce 100 moles of this, you would have written your 100 moles down here, and I said, skip some space, right? Leave some room for work, because now we're going to fill that space. The problem says the chemist needs to produce 100 grams of gallium trichloride. 100.0 grams. Using the following reaction equation, how many grams of gallium and how many grams of hydrochloric acid are necessary to accomplish this. Okay? Now, again, if we'd been given how many moles and asked to compute how many moles, we could now do this pretty readily using the stoichiometric coefficients and how they relate to one another. The question doesn't take us to that point. It gives us a couple more steps we have to do before we can do that. We're still going to relate molecules to molecules based upon the mole ratios. That's how we go from one molecule to another molecule, but not from mass to mass. So as I said before, I kind of alluded to that we're going to have some vertical components to our solution diagram as well. Vertical and vertical. And we're going to have some horizontal components. And in that horizontal component, we're still going to have a ratio. Okay? We're still going to use the mole ratios of our stoichiometric coefficients to relate one molecule to another molecule in the balanced reaction. Over here, and this is one of those diagrams that I hope you'd be able to reproduce on a quiz, for example, where you have a mass and you have moles and you have the mole ratios. And then you have moles, and now you have mass. So if given moles and solving for moles, all we're doing is working horizontally, relating moles of a given times a ratio to end up with moles of an unknown. If we're given mass, we need to move it from mass to moles so we can go laterally from moles to moles. We may be given grams and asked to solve for moles, in which case we would do part of this symbol. If we're given mass and solving for mass, we've got to go the whole U. In this case, and we're going to put our arrows in the direction of movement, we're going to be going from mass to mass. In this case, we get rid of these arrowheads because we were given a mass and we were asked to solve for a mass. Actually, two masses. We'll just do the gallium first and then we'll solve for hydrochloric acid as well. In this particular equation, we do know the mole ratio. We're moving from here, gallium trichloride. It has a 2 in its stoichiometric coefficient of the balanced reaction equation. And over here in gallium is a 2 as well. So we know that it's a 1-to-1 relationship, right? However much gallium trichloride we produced, we need that same number of moles of gallium to produce it, since they have a 2-to-2 or 1-to-1, if you simplify it, mole ratio, 1-to-1. The question is, how many moles of gallium trichloride do we have? We can't solve across here until we get there. We need to move vertically, moving from mass to moles. Once I get to moles, I can convert it to moles, and then I'll have to take moles and convert it back to mass. Do you remember, as we discussed this diagram before, what the translator is? What is this process of moving from mass, in this case, from mass to moles? Okay, both of these are going to use molar mass in some way, right? To go from mass to moles, we're going to interact with the molar mass. And in this case, to take it from mass to molar masses, we're going to divide by. So to go from mass to moles, to go downward, is always going to be a division by the molar mass. I have a certain mass. If I divide it by the molar mass, it produces the number of moles. And anytime on our diagram we move upward, if we move from moles to mass, We're also going to interact with the molar mass. And an upward movement as we go from moles to mass is going to be to multiply by the molar mass. So this isn't multiplying because it's the first one or the second one or it's the reactant side or the product side. It's going to be a flow from what you know to what you're looking for. If you're given the mass of something that's known, you need to first of all divide it by the molar mass to figure out the number of moles. And then you're going to move from the number of moles of that item to the number of moles of the other item by using the mole ratio. And then, given that number of moles, you're going to multiply it by the molar mass of that atom or molecule that you're solving for to get it back in terms of grams. So, we've got the mole ratio. We don't know the number of moles, but we can't get the number of moles until we start solving using the molar masses. In this case, the molar mass of gallium, and over here, the molar mass of gallium trichloride. So that's the question. What is the molar mass of gallium trichloride? How would we figure that out? Periodic table, we're going to look at the atomic masses. We're going to add up the atomic mass of 1 gallium and the atomic mass of 3 chlorines. And when we do that, we add those all together and we're going to get 176.2 AMU. There's 176.2 atomic mass units in a molecule of gallium trichloride. We also know then that there are how many grams in 1 mole of gallium trichloride? 176.2. Right, it's the same number, different unit, 176.2 grams per mole. So in order to figure out how many moles I have when I have 100 grams of gallium trichloride, I divide 100 by 176.2. And this is all example 8.6 in your book. But the result of that is 0.5675. Yep. I have 0.5675 moles of gallium trichloride. Because I was given a mass, and to convert from mass to moles, I divide by the molar mass of that molecule. So I now know I have just a little bit more than half a mole of gallium trichloride. Now, to make this amount of gallium trichloride, we need to solve for how many moles of gallium would I need. Again, the relationship is 1 to 1, so it's the same amount. So to make 0.5675 moles of gallium trichloride, I require 0.5675 moles of gallium. I was asked to solve for how many grams of gallium do I need, not how many moles of gallium do I need. So I've related moles to moles. Now I need to convert from moles to grams. To make 100 grams, another way to say that, to make 0.5675 moles, I need 0.5675 moles of gallium. Or, put in another way, multiply by the molar mass of gallium. What's the molar mass of gallium? Well, again, go to the periodic table, and you would find that gallium has a mass, a molar mass. It has an atomic mass of 69.7 AMU, meaning that it also has a molar mass of 69.7 grams per mole. So to figure out how many grams of gallium I need, I'm going to multiply 0.5675 moles times the molar mass times 69.7 grams. And that comes out to be 39.6 grams of gallium. See? Using stoichiometry, I can move from moles to moles. Stoichiometry allows to do all of my horizontal movements. Relating it by molar mass allows me to do the vertical components. The vertical components. So, we were also asked to solve for how many grams of hydrochloric acid. Now in this case, I'm going to go ahead and write it inside, since hydrochloric is kind of inside the box. I'm going to go ahead and do it this way because I'm going to have a different mole ratio, right? I've got to have a different ratio here to that direction there. I already know that I'm producing 0.5675 moles of gallium trichloride. I've already solved for that. I can use that number again. What's different is this ratio. And what is that ratio? Okay, it's 6 to 2, which reduces to 3 to 1, right? It's 6 to 2, which reduces to 3 to 1. I need 3 times as much hydrochloric acid as is produced in terms of moles. Does that make sense? 2 times 3 is 6. Yes, it makes sense. I can now say that in order to produce 0.5675 moles of gallium trichloride, I need to have 3 times as much hydrochloric acid, or 1.703. Moles of hydrochloric acid. Okay. I get that because I need to produce 0.5675 times a mole ratio here of 3 to 1, which gives me 1.703 moles. But I was not asked to solve for moles, I was asked to solve for grams. So I need to move from moles to grams, and I do that by multiplying by the molar mass. And I multiply by the molar mass of what? What am I going to multiply this by? The molar mass of the molecule I'm solving for, and the molar mass of hydrochloric acid. So molar mass of hydrochloric acid, well, the molecular mass, we've got 1 hydrogen, 1 chlorine. It's 36.5 AMU per molecule, which also means it's 36.5 grams per mole. 36.5 grams per mole times 1.703 moles results in 66.2 grams. So, having the balanced reaction equation gives me my stoichiometric coefficients. They relate my moles to moles. And I can move from grams to moles by relating it to molar mass. And I can move from moles back to grams by, again, relating it to the molar mass. Moles to grams by multiplying by the molar mass. Grams to moles by dividing by the molar mass. That's the module, just so you know. This is the culmination right here. Because we seldom work from moles to moles other than computational, but practical, we work from grams to grams. This vertical step of relating moles to grams by use of the molar mass is the key for us when we're in the lab, when we're doing experiments. How many grams of this and how many grams of that would we need to produce a certain amount? If you notice on page 8.1, or excuse me, page 292, figure 8.1, I've got this cute little diagram of a balance, and then arrows that go to the mole, and another arrow goes to the mole and goes to the balance. That's where I came up with this vertical parts of this diagram. I saw this and went, yeah, let's just convert grams to moles, moles to moles, moles to grams. Okay? So this process is rooted in this diagram. We're going to go over this again tomorrow, example 8.7, when we start. Have a good day.